So judging from how we did with our quiz, using the solubility chart, not terribly difficult, but we're going to quickly go through these 8 before I move on to telling you the other half of that lesson I didn't get to on Friday, which is the polar nature of water, okay, and that kind of stuff. So again, if we want to use this solubility chart, we look for the negatively charged ion in the top row. If it's soluble, it will appear, the metal will appear in the second row. If it's not soluble, it will appear in the third row. So if we're looking at that first one, calcium sulfate, okay, I would find sulfate, which is right here. It is soluble with most things, but calcium is listed right there. Okay, so that stuff would be not soluble. Potassium hydroxide, OH listed here, and it says soluble with group 1 ions and ammonium. Potassium is in group 1, so that's soluble. Lead 2 chloride, so we find chlorine, it's right here, soluble with most things, but lead 2 plus is listed in the third row, so that stuff is not soluble. For number 4, tin fluoride, okay, or tin 4 fluoride rather, we got fluorine right here. Okay, soluble with most things, but not with these. Tin is not listed here, so tin is part of most. Oh, can someone just open the door for him there? Forgot to unlock it this morning. Thank you, Eric. All right, so tin is, so that one, tin fluoride, is soluble. For number 5, copper 2 sulfate. Okay, we find sulfate. Sulfate's right here, soluble with most things. Copper's not listed in the third row, so that stuff would be soluble. Potassium bromide. Bromine is right here, soluble with most things. Potassium's not listed in the third row, so that's soluble. Silver fluoride. Fluorine's right here, soluble with most things. Silver's not listed in the third row, soluble. And beryllium nitrate, all nitrates are soluble, okay, except with these incredibly rare things I've never even heard of, okay, so that one is soluble as well. Okay, everybody good with those? Harry, you can. Let me unlock the door though so you can get back in. Okay, any questions on the solubility chart then? Okay. All right, so this is the second part of the lesson from Friday, and it's about the structure of water and why water's structure basically makes it the exception to every rule. All right, so for example, what do most things do when they cool? Okay, I walked right into that one. I'm thinking expansion or contraction when they cool. Contract. Okay, what does water do when it cools? It expands. Okay, it's one of very, very few things. The only thing I can think of off the top of my head is water. Okay, that actually expands when it freezes. Most things get, okay, definitely smaller in their solid form. Okay, which means water does something nothing else does. Its solid form. Its solid form floats on its liquid form. For everything else, the solid form is more dense than the liquid form. It sinks to the bottom. Okay, if I had, like liquid mercury and a chunk of solid mercury, and I dropped the chunk of solid mercury in it, it would fall right to the bottom. Okay, in most situations, water being the exception, okay, the solid form of a material is more dense than the liquid form. But because water expands when it freezes into ice, it's less dense, and thus it floats. And this is extremely important for life on Earth. If ice was more dense than water and behaved like everything else, lakes would freeze from the bottom up. Okay, which would mean they would freeze solid from top to bottom. Okay? Because ice floats on top of water, the top of the lake freezes first, provides a protective layer of ice between the outside air, which can be very cold, and the liquid water underneath, okay? Meaning that there is still a liquid water environment where aquatic organisms can overwinter and survive. Now, The Titanic would not have been a big problem. It would have survived its maiden voyage if water's solid form, ice, was more dense than its liquid form, because the iceberg was sank to the bottom, and then wouldn't have been a problem. Okay? But it doesn't. Okay. Everyone with me on that? Okay. So the reason that water does these things is because of its molecular structure. So we all know that water has 2 hydrogen atoms and 1 oxygen atom in it. Okay? What we don't realize about that is what happens with the electrons. All atoms have a different ability to attract and hold on to electrons. Okay? It's called their electronegativity, and it's one of the numbers that's listed on your periodic table. So if you're looking at your periodic table, okay, electronegativity is the small number directly above the element's symbol. Okay, so for iron, it's 1.8. For oxygen, it's 3.4, which is really high. Okay, what that means is oxygen can really hold tightly onto electrons. So when we talked about molecular compounds where electrons are shared, that sharing isn't equal. Somebody gets to share the electrons more often than the other. Okay? And that is the more electronegative part of a molecule. If you look at the electronegativity of hydrogen, it's 2.2, which is considerably smaller than oxygen's at 3.4. So what happens is when water forms, and there's 2 hydrogen atoms and 1 oxygen atom, the electron from the hydrogen atom spends more time hanging around the oxygen atom than it does around the hydrogen atom. So its orbit doesn't really look like it's drawn here. It looks more like this. So it goes around the hydrogen atom, yes, but it spends way more time down here closer to the oxygen atom. Because that electron occupies, or there's 2 of them actually, 1 from each hydrogen atom, because those electrons occupy this space, they actually force some of oxygen's electrons down, because all electrons are negative, and like charges do what to each other? They repel, they push apart. So having these 2 extra electrons from hydrogen hanging out in the top part of the molecule pushes some of oxygen's electrons down here. Here's what that does. It makes 2 positive points on the top of the molecule and 2 negative points on the bottom. So what we end up with is water being almost like a charged particle. It has a positive end and a negative end, or rather 2 positive ends and 2 negative ends. Okay? It's almost got kind of 4 poles, hence the name polar molecule. Okay? Just like Earth has a north and a south pole, okay? The water molecule has a positive and a negative pole. It actually has 2 positive poles and 2 negative poles, but okay, it works kind of that way. So the top of a water molecule is positively charged, and the bottom of it is negatively charged, because the electron sharing isn't equal. Okay? It doesn't mean that the molecule itself is charged. It's not. Okay? All the electrons are still accounted for. There's as many electrons as there are protons. It's just where they are leads to positive part and a negative part. All right, so this is what we were talking about. The sharing isn't always equal. Some elements are more electronegative than others, and those covalent bonds where the electrons are shared are not an equal sharing. So what we see is that water molecules, because they're polar, can actually attract and bond to other water molecules. Okay? So this positive end of this water molecule is attracted to the negative end of this water molecule. And they'll pull each other, like they'll attract each other towards each other, and then they'll form what's called a hydrogen bond. Now, hydrogen bonds are not strong. They're very, very weak. Okay? They can break, but they can reform very easily. Right? So they break, they reform, they break, they reform. Right? This is what allows us, or what allows water to do some of the things we see. For example, can you fill a glass of water slightly more than full? Yes, you can. Why? What's that stuff on the top called? Yes, it is. I walked into that one too. Okay? Why does the water fill over the top? Because of surface tension. Okay? Surface tension is the result of hydrogen bonding. You can fill it right to there, but is that very strong? Like if you touch it, does it spill? Like right away. You break the surface tension as soon as you touch it. Okay? And it goes. So hydrogen bonds are there. They can form this surface tension, which is almost like a film on the top of the water, okay? But it's not very strong, it can be broken easily. It's also why water clings to the sides of things, right? If you ever kind of noticed, okay, water can kind of, inside of a container, if you had a narrow container, water kind of does this, and it clings to the inside of the container. Or if you get water condensing on the outside of a glass, the droplets will actually stick to the glass and not run down until they get kind of to a certain size and then they fall. Okay? That's all because of this hydrogen bonding. Water can bond to itself and create surface tension, or it can bond to other things with hydrogen bonds and stick to them. Okay? All right. So the water molecule is shaped kind of at a right angle. It allows 4 points of attachment for hydrogen bonds to occur. So one water molecule can bond to 4 other water molecules via hydrogen bonds. Okay. The expansion part has to do again with water being a polar molecule. So liquid water, as it cools, does what all substances do. It contracts until about 4 degrees. Once it gets to 4 degrees, the water molecules start to repel each other. Because as you push them closer, the negative ends and the positive ends start getting too close to each other. Okay, that is, the positive ends get too close to other positive ends. And just before it freezes, there's almost this elastic rebounding effect that occurs. Okay, they're getting closer, they're getting forced together, and then bang, they go apart and they freeze. Right? And so water expands when it freezes. And we all know that. We've all frozen something in the fridge, or in the freezer, not in the fridge hopefully, okay? And when it froze, it like cracked the bottle or the container or whatever because we didn't leave room, okay, for it to expand. All right, everybody okay with that idea? And again, that's why ice will float on water. This is ice, okay? Way more space, way less dense. That's liquid water, okay? Very rare for the liquid form of something to be more dense than the solid form. Okay, so there's 2 kinds of hydrogen bonds. There's hydrogen bonds that occur between molecules of the same material. So that would be water to water. Okay? If that happens, we call it cohesion. Okay? So cohesion is due to hydrogen bonding, okay? And it's between water molecules. So one water molecule bonds to another water molecule. That's cohesion. That's what causes surface tension. Okay. If hydrogen bonds happen between water and something else, another polar molecule, and there are other polar molecules, okay, then we call it adhesion. And that's where you would see like water sticking to the side of a glass, okay, or to the leaf of a plant, or to the surface of a freshly waxed vehicle. Okay, so if you've ever like taken your car to the car wash and like waxed it, okay, you see that the water like beads and sits on it and it kind of runs off instead of just kind of spreading. Okay, and apparently you can do this. I tried one afternoon. It's 3 hours of my life I'll never get back. But apparently you can do this. I never succeeded in it. You have to bend the sharp edges of the paperclip up, but apparently you can get a paperclip to sit on the meniscus of water. I must have too shaky hands, but I couldn't make it work. Okay? All right. Now, here's an example of a living organism using these polar properties of water. Trees and all vascular plants have to transport water from their roots to their leaves. If we're talking about a giant redwood or a sequoia or some really tall tree, that could be 100 meters vertically. And they don't use any energy to do it. There's no pump in the roots that's squeezing the water up the plant. Okay? All that's happening is as water evaporates from the leaves, it's hydrogen bonded to other water molecules. So as it goes out the leaf, it pulls on all the other water molecules that are in the little tubes called the xylem that run down the plant, okay, that carry the water up. All right? So every single water molecule, if we look at it here, okay, they are cohesively bonded to each other. They will exhibit adhesion to the side of the xylem or the side of the tubes, okay, but they're all connected all the way down to the roots. So when one of them evaporates and goes out of the leaf, it creates a pulling force on all the ones down the leaf. Okay? So as one goes, it pulls the others up. So it requires no energy for the plant to pull the water, to make the water go from the roots to the leaves. It's all accomplished by the polar nature of water, okay? And the fact that they bond to each other. Did anyone ever play with like the barrel of monkeys when you were a kid? Like the little plastic monkeys and you hook the legs and arms together? That's kind of what happens inside the xylem of a tree. Okay? Is all those water molecules are loosely bonded to each other. Things can disrupt that, okay? But those hydrogen bonds can reform easily. Okay? So they'll break, okay? They'll reform, they'll break, they'll reform. Okay? But they're always there. They're bonding to the inside by adhesion. They're bonding to each other by cohesion, and that keeps them all in there. Now, those tubes have to be really small. Okay? They're microscopic, in fact. If they were big tubes like this, the weight of the water in that column would be too much for the polar nature, for the hydrogen bonds to support, so the tubes are all microscopic. There's millions of them in the trunk of a tree. Questions on polar nature of water. So here's what you need to know about polar nature of water. What it means to be a polar molecule. Right, so the electrons are not shared. One end is positive, one end is negative. Okay, that's what it means to be a polar molecule. What behaviors a polar molecule can exhibit? Cohesion and adhesion, because of hydrogen bonds. Okay? Those two behaviors happen because of hydrogen bonds. Okay? And an example of a living thing that's harnessing the nature of water to survive. Okay? And you could, in that case, you could talk about a tree, or you could talk about the fact that that ice floats on water, and that allows aquatic organisms to survive through the winter, whatever. Okay? Something that says, because water does this, organisms live. All right? Other organisms that use this, anything that can rely on the surface tension of water, okay, to survive. So lots of aquatic insects sit on top of the surface film, okay, of water, and they just float on top. Okay, so any types of flies or other types of bugs that might be on a water body that can just sit on the top, they're just sitting on the surface tension of the water. Okay, the Jesus lizard, okay, it can run across small bodies of water. If it goes fast enough, same thing. It just goes fast enough that it doesn't really break the surface tension too much, and it can survive, okay, and get across. Okay, questions on that stuff? That was good there? Okay.